Good evening, students.
Good evening, sir.
So,
Evening, sir.
okay, thank you. Am I audible to you all clearly?
Yes, sir.
Yes, sir.
Yes, audible, sir.
Okay, thank you. So, um, welcome to all to this online platform, which is related to your theory classes in postgraduate diploma in analytical chemistry program conducted by IGNO Regional Center Bhubaneswar. And today is the sixth day of the last paper discussion, MCH-004 paper, and today we will discuss the unit from your block 4, and if time permits then we will move to block 5 of your paper, which is related to your radioactivity, or that is the nuclear chemistry part. So before that we will have the last part of block 4, that is related to your differential thermographic analysis, and uh, followed by your DSC, and the last one will be the thermo titration. And till now we will already discuss the um, units related to your electrogravimetric analysis, sorry, electroanalytical methods, which include your potentiometry, pH metry, conductometry, electrogravimetry, then amperometry, polarography, voltammetry. Then yesterday we have discussed the thermogravimetric analysis, and today we will, and also the application related to these electroanalytical methods. So today we will have the unit related to differential thermal analysis, that is DTA, and followed by the rest parts. So I am sharing my screen with you. Is it visible, students, the PowerPoint presentation?
Visible, sir.
Yes, sir.
Okay, okay,
Yes,
thank you,
sir.
thank you. So I am maximize my screen. So it is now in big size. So this is your differential thermal analysis. In short, it is DTA. And yesterday we have discussed the thermogravimetric analysis, that is TGA. That is the difference in mass with respect to time was determined in TGA, thermogravimetric analysis. That was gravimetric because these are the quantitative analysis or the analysis by weight. And here what happened in differential thermal analysis, here it is written it is differential. So differential means it must be compared with some standard. So that makes it a differential. With respect to a reference sample, we will determine the physical or chemical parameters for our sample. And this comparison is known as the differential. So here we can determine the differential of what? This is the thermal. Thermal means it is in terms of heat or in terms of temperature. So what is the differential of temperature? That will be analyzed by a machine or an instrument which is known as DTA, differential thermal analysis. So here it is written, there is the material under study. This is the sample, stands for S, and one reference, that is R. So both are undergoes an identical thermal analysis. That means both the samples, that is the sample under investigation, as well as the inert sample, inert reference sample, that is S and R, both are undergoes identical thermal cycle, that is the identical thermal condition. So what happen, there will be change in the change in the state of the material, that it may be melted, it may be evaporated depending upon the state or the boiling point or melting point of the sample we have under investigation. So the this one is this thermal analysis is done with respect to or as compared to an inert sample placed in the same thermal condition. So, if the sample gets there will be two types of phenomenon may be happen, or it may be an exothermic process or an endothermic process. If exothermic process or exothermic mechanism happen, then then the temperature of the system will rise. So there will be a change in temperature or difference in temperature with respect to the reference, that will be delta T. That means here the temperature of the sample will rise, uh, and the temperature of the reference will remain the constant, or it will be less as compared to the temperature of the sample, because Ts is the temperature of the sample for an exothermic process where temperature rises, or there will be generation of heat. Okay, so Ts minus Tr will be delta T. In the same way, if endothermic reaction happen, then what happen, endothermic means it is gain of heat or absorption of heat for the reaction to carried out. So if absorption of heat occur, then the temperature of the reference will be more than temperature of the sample. So at this stage, the delta T is also the difference in temperature between reference and the sample. So this difference in temperature, okay, so this difference in temperature will be plotted against the heat applied or the temperature applied, and this will be your DTA curve. And from that curve we may have different type of conclusions, which we will see in our later part. So it is given thermocouple, which is the heating element in the furnace. Thermocouple measuring respective temperature of sample and reference material exposed to the same heating or cooling schedule. So heating means it is exothermic, cooling means it is endothermic, absorption of heat via symmetrical arrangement in the same furnace. So both the sample and the reference were placed in an identical condition, thermal condition. The difference in temperature profile of sample and reference as the cycle progresses also recorded. Then just see, this is the plot, and we can see that where we can see that it is delta t, it is delta t versus time. Okay, so here what happened, now it is the temperature of the reference, it is the temperature of the sample, and it is the temperature of the melting, Tm. So this is just a TGA plot, gravimetric plot. And if I put it in DTF plot, that is differential thermal analysis, then it is del T versus time. So here, as melting is happening, that means what happened? That means what happened? Here from this point, the temperature will slow down. The temperature will decrease. So this is gradually decreasing. That means this point, this point is highlighted here. So this will decrease. So this will decrease. Again it will increase. Again it will increase and remain parallel. So the second curve, this one is the DTA curve, but first one is the TGA curve, thermogravimetric analysis. So when this downward curve is observed, downward curve is obtained, then this will be the endothermic process. When upward curve is obtained, this will be the exothermic process where heat will generated. So here it is written, when sample experiences energy change associated with a physical or chemical phenomena, the difference in the temperature profile of S and R identifies the transition. So it is the difference between the temperature of S and R. If, for instance, the sample melts, its temperature will lag behind. Yes, if meltings happen, that means it's endothermic process, and the the temperature will lag behind. Just wait. So we have that here there are two plots, that is your TGA curve as well as the DTA curve here. So just remember one thing, when there is decrease in temperature, that means it is endothermic, and when there is increase in temperature, it will be exothermic. So for decrease in temperature, the reference temperature will be higher than sample temperature. For when the temperature rises or increase, what happen? The sample temperature will be more than the reference temperature. So by this method, we can have many conclusions from the DTA curve. And here it is written, that is delta T against time. This is delta T against time, or more often the sample temperature. The curve shows an endothermic peak. So as I already told you, that this is the endothermic step. That is the temperature downs or decreases because of the melting or the absorption of heat by the sample. So the temperature decreased with respect to the reference. So this is the plot for your endothermic process. So similarly, we have these things. There is a comparison between TGA and DTA. So this is thermogravimetric analysis and differential thermal analysis. So in TGA, that is thermogravimetric analysis, we have the plot like this. That is, here there is a mass loss, that is calcium oxalate monohydrate loses water to give calcium oxalate, which is again loses carbon monoxide to give calcium carbonate, which is again loses or carbon dioxide to give calcium oxalate. This type of reactions will be there, and for different mass losses, we have the type of plot like this. That means here there is a mass loss, and here there is a mass loss in TGA. But in DTA, we have the change in temperature, that or the difference in temperature with respect to the time. So if the temperature downs or decreases, it is endothermic, and if the temperature increases, it will be exothermic. For endothermic process, the sample temperature is less than reference temperature, and for exothermic process, sample temperature is more than the reference temperature, right? So here this is the endothermic, but here this is the exothermic. Okay, so here it is written, and DTA peak is also the change in heat. It is in thermodynamics. It is known as enthalpy change. So what is enthalpy? It is the total heat content of a system, that is known as enthalpy, right? So if the total enthalpy, it is denoted as capital H. Enthalpy is denoted as capital H, and it is equal to E plus PV, where E is the internal energy and PVR is the PP work done by the system, or P is the pressure and V is the volume. So it is the enthalpy that is denoted as capital H. So just you should remember the heat in thermodynamic concept. It is known as enthalpy, and I symbol is capital H. So lowering the heating rate, reducing sample weight, sharper peak with improved resolution. So these are the factors on which the DTA curve depends. That the lower heating rate should be lower. That means a sudden high rate of heat will not be effective, and will not give a sharp peak. Then we have a sample weight should be minimum. Okay, then we will have the result is sharper peak. So while TC only measure change in mass loss, DTA will register change in material where no mass loss occur. The crystal structure changes, melting, glass transition, etc. So in DTA, there may or may not be a mass loss, but uh, there will be changes in the material, like the crystal structure, the melting, boiling, glass transition. These types of things can be concluded from your TTA curve. Then we have what are the different phenomenon causing change in heat or temperature. We have some physical phenomenon like adsorption, where exothermic process occur, desorption, where endothermic mechanism may happen. So for endothermic here, this is otherwise known as cooling effect. This is the exothermic, it is the heating effect. So when adsorption is happening, that means the foreign adsorbate materials are settled on the surface of adsorbent. So that is the exothermic part. Similarly, in the endothermic, we have desorption, that is detachment of the adsorbed molecule on the surface of the adsorbent. So this is known as desorption. It is just the reverse or opposite of the adsorption. So then change in crystal structure, then crystallization, melting means it is endothermic, vaporization, then sublimation. So these are the physical phenomenon on which the DTA depends. So like this in chemical, we have oxidation, reduction, breakdown reaction, chemisorption. So this is related to your physical phenomenon. Sorry, this is related to your adsorption, adsorption with chemical bond. So this is chemisorption. If adsorption is mainly of two types: physical adsorption and chemical adsorption. Physical adsorption is known as physisorption, and chemical adsorption is known as chemisorption. So this is happening due to the formation of chemical bond between the adsorbate molecule with the surface of the adsorbent. So this is known as chemisorption. Then at the end we have solid state reaction. So these are the phenomenon on which the DTA depends. So we have crystallization, exothermic, melting is endothermic, then peak orientation either up and down in DTA thermogram depend on instrument manufacturer. The DTA experiment tell us that something is happening at a specific temperature, They usually do not tell us what is happening. Combination with other methods like X-ray diffraction, spectroscopy, microscopic investigation, and composition analysis like electron probe microanalysis, that is EPM, are required to interpret the result. So by DT experiment, we can predict that due to the change in temperature or heat, some changes are some changes are happening in the material, but we are not able to trace out what are the exact conclusion, or what are the exact phenomenon that is happening in the material. So this is just an disadvantages of your DTA. So this is the second part of our discussion, that is differential scanning calorimetry. So we have this is in short, it is DSC. So a DSC measures the difference in heat flow. So this is related to the heat flow, that is MW equal to MJ by second. That is if this is your milliwatt equal to millijoule per second between a sample and an inert reference as a function of time and temperature. So as this is differential, so this is again sample and reference, and we have one calorimetry here which is related to some scanning. Then it is the difference between the heat flow, and in DTA it is difference in temperature, but here this is difference in heat flow, and with function of time and temperature. So we have um, uh, two holders here. One is the reference holder and second one is the sample holder. So it sends the reference, it sends the sample, and you should remember in DTA or in DSC, the reference generally used is alpha alumina, that is aluminum oxide. It is generally used as the reference for DTA or DSC. So an empty pan on the reference sensor should react similarly to the pan on the sample sensor, thus cancelling out any pan contribution. So that means this is just a balance. This is just like the thermobalance, where there are two pans, one having two pans of same weight. So the null position will be at the middle, and when this will contain the reference and this will contain the sample. Then sample sensor, heat absorbed by the sample gives an endothermic response, heat released by the sample gives an exothermic reference. So this is a sample pan which senses the heat absorbed or heat released. If heat is absorbed, this will be endothermic. If heat is released, it will be exothermic, which is very much sensible uh, with the heat flow rate. Okay. So then we have type of DSC. What are the type? We have heat flux DSC. This is quantitative DTA. Then power compensated DSC measures enthalpy change and compensates heat release or gained during thermal analysis. So this is your power compensated DSC, and this is your heat flux DSC. So where two pans are here, sample and reference. We put the reference as alpha alumina and our sample. Then these two will analyze at is same that is thermal condition. Then there will be change in temperature. This include in this is your quantitative DTM, that is heat flux DSC. But in power compensated DSC, what happened, that platinum sensors are here. These are the individual heaters, that is coil. So we have two cells, that is a sample cell and reference cell, and these two are separated. This is not connected. Okay, these two are separated, and through this, we can measure the temperature change of the sample, whether the temperature which we have supplied that will decrease or increase. It depends on the heat release or heat gained by the sample. Okay. Similarly, the reference will be analyzed. So if it is heat gained, it will be endothermic. If it is heat released, it will be exothermic. So for heat release, the net temperature will be higher than the reference. If from the sample heat is observed, the net temperature will be less than the reference. So if it is observed, then the concept of melting is there. If the heat is released, the concept of boiling or evaporation will be there. So this is the heat flow, that is change in enthalpy dH by change in time. This is the DSC heat flow signal, and Cp is the heat capacity at constant pressure. This is Cp. So what is heat capacity at constant pressure? So how much temperature we can supply to a system that will raise the temperature of the system by 1 degree centigrade for 1 molar concentration at constant pressure. It will be Cp, that is heat capacity at constant pressure. And there is a concept that is also Cv, that is at constant volume. So here dH by dt is Cp, and if it is change in internal energy by time, this will be Cv, that is heat capacity at constant volume. That is not required for you now. And the concept of heat capacity at constant pressure, that is Cp into dt by dt, that is change in temperature but with change in time. So this will be the formula, that is change in enthalpy with time equal to heat capacity at constant pressure into heating rate, that is change in temperature by change in time. So the Cp will be sample heat capacity, that is heat capacity at constant pressure. It is equal to sample heat capacity, sample specific heat into sample weight. This is the formula. So heat flows into the sample as a result of either of these things. That the heat flows into the sample, that means this is absorption heat, and this is heat flows out of the sample, that means it is release of heat. So if it is absorbed, then melting will be there, transition will be there, heat capacity will be there, and these are endothermic processes. But here what happened, these are exothermic processes because heat is out. It may be oxidation, curing, crystallization, heat capacity, these things will be there. This is the polyether ether ketone, PEEK. So this is just a polymer example, and in the DSC plot we have this type of plot. So from this we can conclude that the first, here there is a transition, and this transition may be the glass transition. Then we have glass transition, means here heat, some amount of heat is absorbed. So this is just like, this is not a exothermic, this is just a transition of the state, that is from solid state to liquid crystal state, that is glass. This is a transition state between solid and liquid. Then suddenly the melting happened, that is absorption heat, that is 169 degrees centigrade. Okay. So from this, again, the, so this is the an endothermic one. So this is wrongly written here. This is not exothermic. This is endothermic, and this is exothermic, where heat is rises 339 degrees centigrade. So this is the crystallization peak. This is the thermal peak. So this is the polystyrene, DSC and DTA. So two types of plots are here. So just see, this is the TGA, right? So blue color is the TGA. Then we have the DSC, this one, the brown color. This is exothermic, and then there is 92.33 degrees centigrade for this one. So this is polystyrene. Then we have polymethyl methacrylate PMMA polymer, and and we have the TC curve as well as the DTA curve here. Okay. Then we have carbon tetrachloride. We have these things. This is just monoclinic to rhombohedral. That means it is the transaction. Then after that, from rhombohedral to cubic, this is also a transition. Then we have cubic to liquid state. So this is just it. So this is for your carbon tetrachloride. This is the DSC response for your endothermic process. Then we have DSC-TGA, the technique. What is the instrumentation part? This is the instrument, and it is a Q600 STT. This is simultaneous DSC with the TGA. So both the analysis can be done by one instrument. So this is simultaneous DSC TGA measure, both heat flow as well as weight change. So heat flow means this is your DSC differential scanning calorimetry, and weight change means it is TGA, thermal gravimetric analysis, as a function of temperature or time at a controlled atmosphere. So simultaneous measurement of these two materials not only improve productivity but also simplifies interpretation of the result. The complementary information obtained allows differentiation between endothermic and exothermic events which have no associated weight loss. Example, melting and crystallization, and those which involve a weight loss, that is degradation. So degradation, weight loss means it is related to your TGA. But when there is no loss in weight and there is melting or crystallization will happen, and there will be no change in molecular formula, only some transition will happen. This will be determined, or this will be predicted from your DSC, differential scanning calorimetry. Then these are the some specification of that machine. That is a DA instrument STTQ600. This is the name. This maximum temperature is 1500 degrees centigrade. Heating rate is per minute 100 degrees centigrade rise up to 1000, and after 1000 it is 25 degrees centigrade per minute rise. That is up to 1500. That is the maximum temperature it can bear. Then this is the sample holder made up of platinum and alumina. This is the reference. Okay, alpha alumina. That is Al2O3 in microliter. Then we have weight sensitivity into zero point 0.1 microgram. It is a micro means it 10 minus 6 gram weight sensitivity. Then the change in temperature or the DTA sensitivity is 0.10 minus 3 degrees centigrade. That is up to from 200 to 1300 degrees centigrade. So for every 10 to the minus 3 degrees centigrade difference in temperature, which will be sensed by the DTA instrument. Then what are the gases, purge gases to make the environment inert? This will be helium, nitrogen or argon. The flow rate, the heat flow rate, it is 220 to 1000 per minute and regulated by a mass flow control with gas switching capability. Secondary purge, we have oxygen, carbon monoxide, carbon dioxide, nitrogen, helium and argon. And this is the flow rate of the gas, that is 10 to 100 milliliter per second. So, what these simultaneous or multi-purpose instrument tell us? It tell us whether the material is under oxidative or thermal stability and what is its composition. If the material is multi-component system, estimated lifetime of product and how much time it can sustain and what is the lifetime. Then decomposition, kinetics of material. This is also an important parameter to know the kinetics. Then we have effect of reactive atmosphere on material, moisture and volatiles content of materials. Then the very important, that is transition temperature from one state to another, from monoclinic to rhombohedral to cubic. These are the transition. From cubic to liquid state, it is also transition. Then heat of fusion and a reaction. Then at the end we have melting and boiling point. So these are the things which can be very effectively determined through DSC and a TGA instrument. So this is the instrument. This is the mm, bisect part of your DSC TGA instrument. So this will have the sample and reference cups here. There are two holder, one sample holder and one reference holder. The sample holder will contain the sample and the reference holder will contain alumina, that is aluminium oxide Al2O3, and this is the gas flow, that is it may be nitrogen, helium or argon. This is the furnace, this is the thermocouple is here, this is the furnace. Then dual balance mechanism here, which will predict if there will be weight loss or not. Then photodiode and sensors, which will have direct effect on the temperature change in a reference as well as in the sample, and which will predict what type of changes, physical and chemical changes happening in both reference as well as the sample. So this is the reactive purge gas. This is the small capillary like tube is here, and from so through this tube, the purge gases are applied, and this is the balance of thermocouple beams are here. Okay, so there are two pipes are they're coming from this dual balance mechanism. So these things are there. Then we have TGA weight calibration using standard weight. This is the machine, this is the calibration. First, the calibration should be done with the standards. So first the weight, standard weight calibration, that is mass loss reference materials will be checked. Then temperature calibration by endotherms of high purity metal like zinc, indium, gold, and Curie point measurement of ferromagnetic materials. These things are used for the calibration purposes. Hello, নমস্কার। ଇଏ ଆପଣଙ୍କ ଲେଖାଟା କେତେ ଦୂର ଗଲା? So we have the temperature calibration through standard zinc, indium, and gold. Then we have Curie point measurement. Then the flow rate and the cell constant. It must be standardized or calibrated using endotherm of high purity standard material, and these standards are supplied by the company with the instrument. So before any unknown sample determination, we should be standardize or calibrate the machine, and then we have a temperature calibration, that is theoretically for zinc it is 419, for fusion of zinc it is 108, for heat fusion of zinc it is 115. So these things are there. It is first this is 420, then it is then that means it is melting point of zinc. It is um, just as the same, that is 419.5 degree. So the standard samples are run to the machine, and the and if the standard the standard are matched with the theoretical value, then the machine is okay or ready for estimation of unknown. Then we have a QD point just like this. This is alumile, means this is aluminum oxide, alumina. We have 152 degrees centigrade. Then we have nickel, that is this is pure nickel. This is 83% nickel and 17% cobalt. This is just alloy. And these things are there. Okay. Then DSC with the TGA. This is stoichiometry data from TGA, that is sodium tungstate. So this material is estimated. This is the TGA plot, the dehydration, and this will be the uh, DSC, that is differential scanning calorimetry, and where there is endothermic here, again endothermic, so there will be absorption of heat. Then these are the comparison of TC, DSC for variety of physicochemical processes. Then we have, so from bottom to top, the mass will increase, and when so so the right hand side is your DSC, and left side this is your TC. Then we have the plots like this. So this is just glass transition. This is just the melting, crystallization, evaporation, sublimation. So this type of plots, these are the standard plots of TG and DSC. So this depends on whether heat is absorbed or heat is released. So what is heat capacity? Already told to you that when it is the amount of heat required to raise or lower the temperature of a material by 1 degree centigrade at constant pressure. It is heat capacity at constant pressure. If it is at constant volume, then this is the heat capacity at constant volume, and it is denoted as capital C. And if it is P means constant pressure, V means constant volume. So Cp is the absolute value of heat flow divided by heating rate, and most DSC do not measure absolute heat flow or heat capacity. So baseline subtraction is required on most DSC measurement. Why it is important? And it is important for thermodynamic property of material, where heat flow is not determined. Heat capacity is a measure of molecular motion. It is a theoretical concept that is molecular motion is responsible for the heat capacity, and it increases with when the motion increases. So provides useful information about physical properties of the material as a function of temperature. Then this is the equation, that is dH by dt, that is change in enthalpy with the time. It is equal to the heat capacity at constant pressure into temperature coefficient, that is dt by dt, where dt is the change in temperature and dt is the change in time. So again the Cp will be dH by dt divided by dt by dt into some constant K. So this is the heat flow, this is the heating rate, and this is the calibration constant. And this constant is different for different company manufacturer or different manufacturer. And where Cp, the unit is joule per degree centigrade. So this is the unit equation. Okay. So these things, this is the theoretical background of your DSC, that is heat capacity into heating rate. So measuring capacity ASTM method, that is American system for testing metals. Okay, so ASTM, and its code is E1269. Minimum 3 runs should be done. Empty fan for baseline, run calibrate, and then sample. So 3 runs are there. Typical method ISO for 10 minutes. That is same temperature for 10 minutes. Then 10 degree centigrade for 1 minute, and then ISO for 10 minutes. Heat capacity measure DSC. We have this type of plot. Just go through this thing. This is according to STM E1269. This is your baseline measurement. This thing is not required. Okay. This is the standard graph, and these are the limitations in measurement of heat capacity. Two identical calorimeter in a common enclosure that are assumed to be identical. The heat flow rate of an empty, perfectly symmetrical twin calorimeter should be zero. However, it almost never is because the DSC is rarely symmetrical as assumed. The symmetry is the inevitable result of manufacturing tolerances and is unavoidable. The resistance between sample sensor and the furnace equals the resistance between reference sensor and the furnace. Measured temperature equals sample temperature. No heat exchange with the surrounding. So these are the limitations. So then we have physical limitations are here. This is exchange of gases, radiation from the furnace, indication of sample temperature, conduction through sample pan and instrument, then convection at the end. So this is the physical limitations. So this is not required. Then literature source is thank you. So after the differential thermal analysis DTA, followed by your DSC differential scanning calorimetry, we have the last part of your unit 11, that is thermometric titration. This is also an interesting electroanalytical method, and this is related to your titration. And here there will be titer and titrant, like acid base titration, where where alkali or base is used as titer, and acid is treated as titrant. So titer is always added to the titrant. In the same manner, we have some titrations, and the change in temperature or change in heat is measured through the titration process. So this is your MCH block for unit 11. Okay. Then we have each chemical reaction involve an enthalpy change, that is the heat change that leads to change in temperature. And if it is if the temperature is raised or increases, this will be exothermic, and if it is decreases, it will be endothermic. Then we have for thermometric titration, the reagent solution, that is the titrant, is added to the sample at a constant rate until attaining the endpoint. That means it is the titrant is added to the sample at a constant rate till there will be endpoint. The endpoint may be the change in temperature, which is the indication that there will be the endpoint is reached and the reaction is completed. The change in temperature of the reaction solution is plotted against volume of the titrant. So here it is the plot of change in temperature along y-axis, and along x-axis it is the volume of titrant added. The titration endpoint can be identified by a break in the titration curve. This is important. So if it is goes linearly and suddenly it breaks, that means the endpoint is reached at that point and can be accurately determined by means of second derivative. As the temperature sensor, that is thermoprobe, will be there in the thermometric titration instrument, has zero point 0.3 second response time and a 10 to 5 Kelvin resolution. Even minutes, even minute changes in enthalpy can be monitored reliably. So these are the advantages of this instrument. Then we have, let us consider a reaction, that is A moles of A and plus B moles of B gives rise to P moles of P, where A is the titrant which is to be added to the sample, that is B, and there will be the product will be P. Okay, so A is the titrant and small a is the corresponding mole, and B is the analyte, that is the sample having small b numbers of mole, and P is the product having small p numbers of moles. Then at completion, the reaction produces a molar heat of reaction. Molar heat means what? It is the heat of the reaction of 1 molar concentration of the sample. It is known as molar heat of reaction, and uh, this is the measurable temperature change, that is del T. So for ideal solution, there will be no loss or gain of heat, and this is for ideal system. But all the systems are not ideal. So for non-ideal system, what happens? There will be increase or decrease of temperature will happen, and if the temperature increase, that will indicate the reaction exothermic, and the delta S, that is molar heat of the reaction, is negative. And for endothermic, which indicate absorption of heat, this will be endothermic, and there will be mm, this will be a positive delta H. So plus delta H, and exothermic will be minus delta H. So this is the thermometric titration curve. Just see here, this is the temperature and this is the volume of titrant added. Here, when the titrant is added gradually, the temperature will rise, and at a particular point the temperature is suddenly decreased by addition of further titrant. So this point, this is the junction point, and this point is now the treated as the end point or the equivalence point of the titration. So from this point we can predict, so how much temperature is the corresponding temperature is determined by just scaling this one. And similarly, this is for your exothermic, where temperature rises, and this is for your endothermic, that is temperature is gradually decreases, and at a particular point this will remain parallel with the axis of the volume of the titrant. So this will be the end point. So this is just the reverse plot. This will be exothermic and this will be endothermic. So in this context, environmental influence, the idealized thermodynamic plot of exothermic left and right, that the previous plot, heat losses are gained from outside the system via the vessel wall and cover, difference in temperature between the titrant and the titrant. There will be difference in temperature. Then we have evaporative losses from the surface of the rapidly mixed fluid. Then at the end we have heat of solution when the titrant solvent is mixed with the analyte solvent. Heat is introduced. Then heat is introduced by the mechanical action of the stirring, and at the end we have the heat produced by the thermistor itself. So these are the different factors on which the thermometric titration depends. Then at equilibrium the reaction lies far to the right, If the equilibrium, if the reaction lies far to the right, then the stoichiometry equilibrium has been achieved. When all analyte has been reacted by the titrant, continuing addition of titrant will be revealed by a sharp break in the temperature or volume curve. So these things are there. Okay. Experimental titration. The shape of the experimentally obtained thermometric titration plots will vary from such idealized sample, and at the end we have some of the environmental influences listed above may have impacts. Curvature at the end point might be observed. This can be due to insensitivity of the sensor. If there is curvature, there is no sharp end point in the plot. If it is curved, so that means the sensor is insensitive, and where the thermal equilibrium at the end point is slow to occur. It can also occur where the reaction between titrant and the titrant doesn't need proceed to stoichiometry completion. Then the determinant of the degree to which a reaction will proceed to completion is the free energy change. It is the effective work done by the system which make the process spontaneous or feasible. This energy is known as free energy. That is, if the free energy change is negative, then we can say the reaction or the process is said to be spontaneous. So for spontaneous, the free energy change should be negative. If this is favorable, the reaction will proceed to completion and essentially the stoichiometry will happen. In this case, the sharpness of the endpoint is dependent on the magnitude of the enthalpy change. This is very important. The endpoint sharpness depends on the enthalpy change magnitude, that is heat change magnitude or temperature change magnitude. It is unfavorable, the endpoint will be rounded regardless of the magnitude of the enthalpy change. Then a reaction where non-stoichiometric equilibria are evident can be used to obtain satisfactory result using a thermometric titration approach. If the portion of the titration curve both prior to and after the endpoint are reasonably linear, then the intersection of tangents to these lines will accurately locate the endpoint. Just see the figure 2, this one. If this is a curve like structure, then we have to extrapolate the the end points from the end points, and this will be the end point of the reaction. This is for curve, and this curve like plot will obtain when the sensor is insensitive, or we have there will be sharp no sharp endpoint will be there. So this type of situation will happen. Then the same thing is a non-stoichiometry type. Then we have the breakdown of temperature here. So this will be the end point of your reaction. Then we have thermosters which have the temperature, which produce the temperature. The thermistors respond quickly to small change in temperature, such as temperature gradient in the mixed titration solution. And signal can exhibit a small amount of noise. Prior to derivatization, it is therefore necessary to digitally smooth the temperature curve in order to obtain sharp symmetrical secondary peak, which will accurately locate the correct inflection point like this. This is the thermistor, okay, and this is very much sensitive towards small change in temperature happen during titration. So this is illustrated in figure 5. This one, the degree of digital smoothing is optimized for each determination and is stored as a method parameter for application every time a titration for that particular analysis is run. So this is the role of thermistor. And what are the application of thermometric titration? We have because of the enthalpy change is a universal characteristic of chemical reaction. Thermometric endpoint thermometric endpoint sensing can be applied to a wide range of titration, that is acid base, redox, where reduction and oxidation takes place simultaneously, or complexometry like zinc with EDTA, ethylene diamine tetraacetate, precipitation like silver to silver chloride or barium to barium sulfate. These are the precipitation type reactions. So, or titrations. Since the sensor is not required to interact with the titration solution, titration is a non-conducting media can be performed, as can titration using reaction for which no convenient or cost-effective potentiometer sensor is available. Then these are demand rapid reaction kinetic in order to obtain sharp reproducible endpoint, where the reaction kinetic are slow and a direct titration between titrant and the titrant. Titrant is the volume added, and titrant is the sample analyte. And not possible, indirect and back titration often can be devised to solve the problem. So catalytically enhanced endpoint. Catalytically enhanced endpoint means it is the use of the indicator can be used in some of the instances, but the temperature change at the endpoint is very small and endpoint would not be detected satisfactorily by the titration software. So it is just a it can be done through catalytically. Then at the end we have the suitability of a particular chemical reaction as a candidate for a thermometric titration procedure can generally be predicted on the basis of estimated amount of analyte present in the sample and the enthalpy of the reaction, as this is the plot between enthalpy and the volume of titrant added. However, other parameters like kinetics of the reaction, sample matrix, heat of dilution, this must have some effect on the outcome or result. A properly designed experimental program is the most reliable way of determining the viability of the thermometric titration approach. Successful application for thermometric titration are generally where titrant reaction kinetics are fast and chemical equilibria are stoichiometrically or nearly the same. And there is examples, and these are some examples, and also in your PDF, I think. Then apparatus and used setup and automated thermometric titration. This is the setup where this is the thermometric apparatus, titration apparatus. This is the burette or microburette used for addition of the titrant, and this is the sample container, and this is the sensor which will sense the heat change or temperature change. These are salient advantages. Easy to learn, the result can be obtained rapidly, solve the issue titrating difficult sample that cannot be titrated potentiometrically, single sensor for all applications, sensor calibration is not required, it is maintenance free, no membrane on diaphragm issues are there, robust technique for routine work, highly suitable for aggressive media. This is automated one. This is A, B, C, D, E. Five parts, main five parts are there. A is the dosing device. B is the sensor. This one is the sensor. B. C is the steering chamber. That will magnetic stirrer will be there for steering. And D is the thermometric titration interface module. Then this module will interface between the physical titration and the digital software or the application software through this computer E. So this will be just an interface. So this is the titration chamber. Okay. Then we have this type the title. These titrations can be determined that is acid base, redox, precipitation, complexometric. Then these are the advantages. These are the more applications. This is sodium hydroxide versus hydrochloric acid titration. That is 1 mole per liter. That means 1 molar solution. Heat of neutralization is 56 kilojoule per mole. So this is highly exothermic reaction. Then more application with weak acid, that is bicarbonate with sodium hydroxide. We have 40.9 heat of reaction. Then we have acid mixture, that is mixture of strong acid, weak acid, and strong base. We have the plots like this. This is a mixture of nitric acid, acetic acid, and phosphoric acid. Then we have titration of acid mixtures. We have these things for nitric acid, acetic acid, and this is phosphoric acid, wrongly written here. And then we have redox titration between permanganate, dichromate, thiosulfate, hypochlorite. This is complex symmetric titration curve. Then we have ETTA curve here in buffer solution, ammonia and ammonium chloride. This is complex symmetric titration of manganese and copper. Then more application is precipitation reaction, silver nitrate, sulfate, aluminum chloride, orthophosphate, nickel, surfactants and non-ionic surfactants. Then we have some miscellaneous titrations also, chloride with boric acid, then with formaldehyde. Then at the end we have the end part, that will be the thanks part. So this is all about your differential thermal analysis with the differential scanning calorimetry, followed by your um, last one, that is thermogravimetric titration. Sorry, this is thermometric titration. So this unit is over, and in the next part of this class, in the second part, we will have in the second part just wait, we will have the last part of your paper, that is very interesting, that is related to radioactivity. And before that we may take a 5 minute break here, and after that we will go to that unit 12, that related to radioactivity. It is in your 10th, 11th, and 12th standard nuclear chemistry or nuclear physics unit is there, and this is just related to that one. And after 5 minutes, we will continue and let's have some refreshment. And at exactly 6:45 p.m., we will have the class. So till then, thank you. Am I audible, students?
Yes, sir.
Yes,
Yes,
sir.
sir.
So thank you. So let's move to the next unit. This is the unit 12 related to your concept of radioactivity. So um, what is radioactivity first? So this concept is related to your disintegration of nuclei. So as we know, an atom is consist of a central nuclear part, and it is surrounded by extranuclear part, as proposed by Rutherford in its famous experiment, Rutherford's gold foil experiment. So in that part, mm, he has also proposed many postulates, and we also know that the nucleus of an atom is consist of proton and neutrons, and electrons are revolving around the nucleus as planets are revolving around the sun. So if a nucleus contain the unit mass protons and and neutrons have no charge but unit mass, and proton have positive charge, positive unit charge, and positive unit mass, then how these positive charge entities or protons and neutral entities, that is the neutrons, are sustained in a closed moiety, that is in a closed nucleus, how these things happen. And there is a concept that is known as a nuclear force. This is just a hypothetical concept that due to the presence of nuclear force, these subatomic particles gets intact within a small volume, that is for volume of the nucleus. And when this nuclear part, that it contain only protons and neutrons, and when this nucleus undergoes undergoes some disintegration, that means division, then due to that nuclear force, huge amount of energy will release. That will the concept of your nuclear fission and nuclear fusion. So if it is nuclear fission, then the concept of atomic bomb is there, and if it is nuclear fusion, then the concept of hydrogen bomb will be there. So like the America attack two atom bombs, nuclear atom bombs in the two cities of Japan, that is Hiroshima and Nagasaki, during I think World War II, I think. So so these small or very minute scale reactions, radioactive reactions, will produce a huge amount of energy, which may be used for the benefit or the destruction of humanity. Okay, so before that, we will discuss what is the concept of radioactivity, and there is a decay law, there is disintegration law, and through this disintegration, what happened? There is production of radioactive particles like your alpha particle, beta particle, gamma particle, or positrons, neutron, proton. These are the radioactive particles. So these particles are very energized particles. Okay, so like your alpha particle, its mass and its charge is just coincide with helium nucleus. What is helium nucleus? Helium nucleus is He24. That means its atomic number 2 and mass is 4. So so the alpha particle or alpha ray or alpha radioactive ray is also having the charge of 2 and mass of 4. So it is same as your helium nucleus. So alpha particle or alpha ray, it is also denoted as He24. Similarly, the beta ray, this is E minus 1 0. That is it is similar to or same as the subatomic particle, that is electron, with a negative charge but no mass. And gamma, it has no mass and no charge, so it is just a null particle or neutral particle, we can say, and is symbolized as Y, that is gamma 0 0, no mass, no charge. And proton, as we know, it is p11, and neutron, it is n01, that is small n. It is 0 means no charge but unit mass. So these things are there. So it will generate radioactive particles or radioactive rays, that is alpha ray, beta ray, gamma ray, proton or neutron. This will be how this radioactivity, what is radioactivity, why radioactivity is a property of a particular atom or element, who discover radioactivity, what are the laws, units, then natural radioactivity, then what is the decay series, classification of nuclides, isotopic and relative atomic masses. Then we have artificial nuclear reaction, and then we at the end we have some mm, measurements of radioactivity, that is gas ionization, scintillation chamber, semiconductor measurement, statistical aspects. So these things are there. Okay, so as I already point out, uh, the radioactivity concept is related to disintegration of radioactive nuclei. What is disintegration? It is the phenomenon of spontaneous emission of radiation or radioactive radiation, such as alpha, beta, gamma, and other forms of the nucleus of an atom. So, from a radioactive nuclei, when disintegration happening, so at that time, what happened? There will be spontaneous emission of radioactive rays, alpha, beta, gamma rays. So alpha ray is just same as your helium nucleus, beta is same as your electron, and gamma is having no mass and no charge, but it is radioactive. So in the next part, we will have what are the objectives. We will distinguish what is radioactive, stable, and or non-radioactive substances. What is the simple laws, unit and correlation between mass and energy? What is natural and artificial radioactivity? What is the decay law? The distinguish between chemical and radioactive equilibrium. Then we have nuclear reaction and preparation of isotopes, radioactive isotopes. Then we have some detectors, that is radio detectors, and in the latter part we have statistical behavior radioactivity, background correction in radioactivity measurement. These things are there. Okay, so radioactivity, this phenomenon of radioactivity was laid down by William Conrad Roentgen in 1869 when X-ray were discovered. But finally, this was discovered by Henry Becquerel. The scientist is here. Just yes, he is the man who discovered the concept of radioactivity. Okay, in the 19th century, after Roentgen, and subsequently in 1896, it is 1895, but 1896, after 1 year, then what happened? The French physicist Henri Becquerel proposed a concept, that is radioactivity. Okay, so before that, let's have some theoretical part. And actually, what happened when what is radioactivity? Now, as I know, every element or every atom in this universe has more than one form, that is known as the isotopes. Like hydrogen, we have proton, deuterium, and tritium having the same number of proton or charge but having different masses, that is different number of neutrons. Like hydrogen proton, it has one proton but no neutron, neutron is zero. But in deuterium, proton is one but a neutron is also one, so 1 plus 1 becomes 2, that is the mass of the neutron. So for tritium, it is proton 1, neutron 2. That is mass is 1, but sorry, that is number of proton is 1 and the number of mass number is 3. That is H13. So similarly, we have the isotopes like K40. This is one isotope because potassium, the atomic number is 19. Its isotopes are K1939, K1940, K1941. So between K1939, 40, 41, this 40 is radioactive. Like deuterium D12, it is radioactive. Carbon has three isotopes: C612, C613, and C614. And between these three isotopes, C613 and C614, this is radioisotope. So like this, the other metals which are which have radioactivity, like cobalt 60, cesium 137, zinc 65, plutonium 239. So these are all radioactive. Okay, so one may ask, sir, how we will know which one is radioactive, which one is not? So it is not possible to remember all these radioactive isotopes by its formula or by its name. So there is a plot. Yes. When n by z value, that means number of neutron and number of proton, when the ratio is equal to 1, this is a stable nuclei. That means it is not radioactive. And when this n by z value is between, here it is written, it is 1.5. Yes, n by z value, it is 111. These are less radioactive. But when it is more than 1.1 to 1.54, these nuclei are considered as the radioactive nuclei. Okay, so this is new this is mm, this is neutron to proton ratio, that is n by z, neutron to proton ratio. Very simple. Okay, so yeah, there is a formula. This is just a general formula. This may or may not be applicable to all the elements or atoms. If the z is even, that means number of proton is even, number of neutron is even, then mass will be z plus n, it is also even. Then in the periodic table, we have this combination of 165 elements which are, which nuclei are stable. That means these are less radioactivity. But when it is even and odd, the Z plus N will be odd. We have 55 elements. This may be radioactive, having the stable nuclei. So similarly, the odd even have 50 and odd have 5. So these are the elements or nuclei which are very much stable on the basis of this combination. So here it is written, for even A with Z and even N, that is mass number, this is number of proton and number of neutron. Largest number of stable nuclei exists. This is 165, largest. When it is even. When it is odd nuclei, there will be even Z and even N. Then same number of stable nuclei will form. For even A and odd Z, odd N, there will be small amount of just wait. Hello,
Sir, namaskar.
namaskar, କୁହନ୍ତୁ। So we have this combination that is known as the n by z ratio that is related to your stability or radioactivity of the nucleus. Then we have, just see here, alpha, beta, gamma ray emission. So if from the bottom we will go, if alpha emission is there, so alpha is same as the helium nucleus He24. That means when a radioactive nuclei releases one alpha ray, that means its its atomic number will decrease by 2 unit and mass number will decrease by 4 unit. So that means it is converted to Y, that is different element. With Z value it is -2 and A value it is -4. And if mass number and atomic number, that is the number of proton, is difference is 2, that means number of neutron is also decreased by 2. So this is the release of alpha emission. When it is positron emission, that is B plus, that means it is E plus 1 0. This is positron, but this is beta emission. This is electron. If it is electron release, this is known as beta emission. If it is beta plus, that means it is known as the positron emission. So positron means it is the opposite of electron, that is the charge is plus 1 but mass is 0. Then what happen, if charge is plus 1, then this charge will decrease by 1 unit but there is no loss in mass. So y z minus 1 a, and the neutron number is increased by 1, n plus 1. So similarly, when beta emission is there, that is emission of electron. Electron is E minus 1 is 0. That means Z will be gained by 1 unit and mass remain constant. Number of neutron is -1. And these product nuclei are known as the daughter nuclei. Okay, so this is the parent, this is the mother or father, and from this, the daughter is get birth. So this type of things are there in radioactivity. Then the discovery, as I already point out, this great man, Henry Becquerel, in 1896, proposed the phenomenon of spontaneous emission of radioactive rays from radioactive nuclei, and very interestingly, these two greats of science, that is Marie Curie and Pierre Curie. This is Madame Curie and Pierre Curie, her husband. They both worked many years in the field of radioactivity, and Marie Curie and Pierre Curie both have discovered the element, that is radium. Radium, for which they awarded the Physics Nobel Prize. And after the death of her husband, Pierre Curie, Marie Curie alone continued the research, and she discovered another element, and she named that element as polonium, because she belongs to the Poland country, the country Poland. So the element name is polonium, and for that discovery, she again awarded with the Nobel Prize uh, in chemistry. So he is the only lady or only human being in the world till now who have got two Nobel Prizes in two different fields. That is in the field of physics and chemistry both, and they work in the field of radioactivity. Okay, so then law of radioactivity. This is just related, same as your first order kinetics. In chemical kinetics, if you remember the things, then there is chemical kinetics chapter is there. Thank you, ma'am. Then there is first orders, zero order, first order, second order reactions are there. When the rate constant, which depends on, directly depends on the change in concentration of the reactant, this will be first order kinetics. If it is not depends on the initial concentration of the reactant, this will be zero order, this type. Okay, If it is depends on the square of the reactant concentration, this will be second order, like this. So just you should remember that law of radioactivity or the rate of disintegration, it is follows or it obeys the principle of first order kinetics. So the rate of disintegration of the radionuclide at any time is directly proportional to number of atoms per at that time. It is written number of atoms. That means it is directly proportional. So when there is disintegration, there is decrease in number of nuclei with time. So the rate is now minus dn by dt. N stands for number of nuclei or number of radioactive atoms with time, minus dn by dt. It is equal to lambda into n, where n is the initial concentration of the radioactive atom, and n and lambda is the disintegration constant. Okay, so this is the disintegration constant, and the unit of lambda, it is second inverse. Okay, so there is another relation, that is n equal to n0 e to the power minus lambda t. This is also obeys first order kinetics. So this is the number of nuclei after disintegration. N equal to n0 is the initial concentration of the nuclide on initial concentration of the radioactive atoms to the exponential of integration constant into t is the time in minus. So this is also one formula which will be helpful in your in solving some problems. Then we have the plot of first order, like n equal to n0 to minus lambda t, number of counts for time, and it is gradually decreases because with time the number of nuclei will be decrease. So that's why this will be the equation. What is the half-life period? It is the half-life period is the time at which half of the initial or half of the initial concentration of the reactant gets consumed or gets disintegrated. This is known as the half-life period. So it is just a time period at which half of the reactant is reacted. So half of the reactant is reacted means it is mathematically it is denoted as T half, and T half equal to ln 2 by lambda, and if it is ln 2, that means it is 2.303 into log 2, and log 2 is 0.3010. If I multiply 2.303 into 0.3010, it will be 0.693 by lambda, where lambda is your disintegration constant. So these things you have to remember. Okay. Then we have second law, it is not needed. Okay, so I just read out this one. Second law of radioactivity was proposed by Frederick Soddy, and it is called a group displacement law. According to this law, during a decay, parent decays to daughter, where Z is decreased by 2 and it is displayed by two groups on the left in periodic table. Similarly, during beta decay, Z is increased by 1 and the daughter nuclide is displayed by 1 position towards the right. So this is very simple, that if I just see this one, periodic table. Yes. Is it feasible, students? Periodic table. Hello? It is
Yes, sir.
visible.
Yes, sir. Visible.
Okay, okay. Okay, so if I go for a alpha emission or alpha ray decay of, let us, carbon. It is atomic number 6. It decay means it will release He24. That means two numbers of proton and loss of 4 unit of mass, loss of 2 unit of proton and loss of 4 unit of mass. Then the carbon 6 becomes, now a new element will generate, that will be less than carbon, that is 4. So that will be 4 means it will be beryllium. So from carbon, when alpha ray is released or decayed, then beryllium nucleus is generated. That means in the periodic table, we we will have two step back. That means 6 becomes 4. And if the same carbon is a decayed electron, that is the beta ray, then beta ray is E minus 1 0. That means the atomic number will increase by 1 u. That means it is right to one step. So this is the second law of radioactivity. It is written when it is here it is written when it is alpha decay, then two groups on the left, it is written na, in alpha decay two groups on the left, that means carbon two groups, one two, it will be beryllium. And if it is beta decay, that is electron release, then it is one position towards right. That means carbon is converted to one position towards right, means it is becomes a nitrogen. Okay, so these things are there in your second law. Then there are units. So to honor the father of radioactivity, Becquerel, Henry Becquerel, and the contribution from Madame Curie, we have different units of your radioactivity. The basic unit is becquerel, that is 1 BQ. It is written 1 BQ. It is same as 1 disintegration per second. In short, it is DPS. This is 1 disintegration per second. And if it is your Curie unit, and this will be 3.7 into 10 to the power minus, so 3.7 into 10 to the power 10 disintegration per second. So these things are there, and your Curie is symbolized as Ci, and Becquerel is Bq. Okay, so we have also mega Curie, that is MCI. Mega means it is 10 to the power 6. If it is micro Curie, it is 10 to the power minus 3. No, I'm wrong. If it is millicurie, it is 10 to the minus 3. If it is micro, it is 10 to the minus 6. If it is mega, it is 10 to the power 3. So these things are there, and here it is a problem also. Then natural radioactivity. And this is the radioactivity naturally imbibed in a nucleus. That is, if we go for the um, periodic table, then just remember the this actinide series. This is very much radioactive, and this series is generally used for radioactivity. That is thorium, uranium, your plutonium, then cerium. This is lanthanide and actinide. These elements are generally used in radioactivity. Okay. So, in the next class, we will continue from natural radioactivity, and hopefully, we will cover up all these things in the last class. And this is the radioactivity series, from which element to which element it will convert. Okay. These things we will discuss, and if any doubt or anything, anyone try to sorry, want to ask or something to share, um, you may proceed, or over to you students. Over to you students. If any question or any doubt you want to ask or anything, you may ask. It's about So if no questions are there, then we may wind up the session here. And in the next class, that will be the last class of your PGDSC program, and in the last block, last unit, and last paper of your program. And hope we will have a nice ending tomorrow. And best wishes to you all from my side and from IGNO Regional Center for your patience, hearing, and cooperation. Thank you, students.
Thank you, sir.
Thank you, Chef.
Thank you, sir.